Good. So conduction in steady state in 1D and the concept of thermal resistance. This is something we have seen and we're finished, and this is just a recap to have a sense of how we landed here. On our first week, we talked about energy balances, heat coming in, heat going out, heat being generated, and all those three together gave us the heat stored. And we saw that this energy balance, we could do it as a batch between two time intervals or as a rate. We also saw that this equation we wrote, that is a very universal equation, makes sense only when we have made a control volume and we have um, determined clearly what the boundaries of that control volume are. The heat in and heat out, we discussed it, but we didn't say how it came in or out. So in our week 2, we said, okay, these are the mechanisms through which heat can come in or out to the control volume. In week 1, we had discussed advection, but in week 2, we discussed convection, radiation, and contact, and conduction. In week 3, we said, all right, let's consider the case in which the conduction doesn't matter because for whatever reason, the temperature inside the control volume is homogeneous and the conduction doesn't really play a role. So every point inside the control volume was at the same temperature. There is a case of lumped capacitance. And in that case, in the equations of our energy balance, our energy rate balance, ended up becoming a first order differential equation that for the case of convection was a linear first order differential equation, which we solved and was very insightful. We could account for the time things take to cool down or the time things take to heat up. We could account for the issues of phase changes, like in the case of making snow. We could account for issues of internal heat generation, like the case of a computer chip that is running with a fan, and what happens if the fan breaks. We could, and we could even, if we wanted, we could do this for radiation. In that case, the differential equation is not linear, it's solved in the book. We didn't go too deep into the complex math, but we said that in many cases, we could use the radiation equivalent convection coefficient and we wouldn't be all too bad. So that was week 3. In week 4 is I put everything that is spread through the book. I put it in all 1 week. That is this week that might have seemed obscure to some of you. That is differential control volumes. If we actually do have gradients inside the body, lumped capacitance doesn't work anymore. So what we need to do is to make a control volume that is so small in the direction of the heat gradient, thermal temperature gradients, such that inside that very small control volume, we can say, yes, it's lumped capacitance, of course, because it's so tiny. And doing that, we did that for a bar that has heat losses by conduction or no losses by conduction, and whether we have advection too. We saw so many things all together, and that is the source of fins, which is in the assignment that you also have due in March. And all those things together, we also looked at we generalized the equation of conduction to the cases of cylindrical and spherical symmetries, which are going to be relevant today, right? But it was all about, all we did during this week 4 of class was make a control volume that was small enough and get a differential equation that represented different problems. We didn't even solve the differential equation, we just wrote it. And that gave us the power of say, hey, all these different problems of real life, we can capture in the form of an equation. And once we have the equation, it's a mathematics problem, but not a problem of engineering. Of course, we still have to solve it. For the simple cases we will do in this class. After that, we got into last week, that was, okay, we have talked about in lump capacitance, what happens when we have a transient but no conduction. And then last week, well, the week before the break, we talked, okay, what happens when we have conduction but no gradient? And we talked about conduction in 1D. So the problem became steady state, no more derivatives against time, but we had derivatives in space. If the problem is 1D, no problem, because it goes back to an ordinary differential equation. Now, in this case, would be a second order differential equation, right? And we solved that equation for the case of a plane wall. And from there, we built the concept of thermal resistance. So let's see the concept of thermal resistance here. Just okay. we end up with an equation like this, that is the very general equation, in this case in Cartesian coordinates. And we're going to use, right after this, you're going to see we use the same equation for the case of cylindrical coordinates and spherical coordinates. But for now, this is what we did the week before the break. We said, this is a general equation. Let's consider a steady state. So in steady state, the transient term would go away. Another thing that was important from when we talked about differential control volumes is let's listen to what the differential equations say. This differential equation has three terms, one on the left and two terms on the right. And each of the terms has a function. Term on the left was transient. The term in the right-hand side, the first one, is conduction. And the third term here on the rightmost term is internal heat generation. So we said, for the case of a wall, let's consider the transient case. Let's consider no heat generation, which we could if we wanted, but we don't want right now. And we end up with this Laplacian equals to 0. But we went farther because we said, well, in the wall, we have if the two walls, the two sides of the wall have different temperatures, but the temperature is uniform on each face, then the heat goes across the wall, but not in the plane of the wall. So if we pick X as the coordinate going across the wall, Y and Z don't matter anymore. And it's a 1D problem. And the problem is all captured by this equation that is second derivative of temperature in space is 0. So that one was very easy to solve because it gives us a straight line. And what we saw is that heat, the rate, Q, is proportional to the delta T, to the difference in temperature between the two sides of the wall. And from there, we could define this concept of thermal resistance using the analogy with electricity. In electricity, voltage is proportional to current, and in heat transfer, temperature difference is proportional to heat rate. So we define the concept of thermal resistance, and we use R to name that thermal resistance. And for the case of a wall, we had an expression that was where we have it. For the case of a wall, was L over Ka, the thermal resistance. And we also have the concept of thermal resistance per unit area. You're going to see later today the concept of thermal resistance per unit length for pipes. So the thermal resistance per unit area, and in this case was L over K. Whatever it was, you don't need to remember it. You can use the formula sheets from previous exams in previous years, or you can have your own notes. But whether you remember it or not, these are very simple expressions, but very powerful, because they enabled us to start dealing with problems that have multiple resistances, like the case of a wall with a stucco layer. right? And we would have now two resistances in series. And how do we know it's in series? It's because the heat goes from one into the other and keeps going. We're going to see in a second, as a refresher, that sometimes resistances go in parallel. So we did this example of a wall with stucco that was two resistances in series. And then we said, aha, because convection also has the same relationship between temperature jump and heat rate, we can define a thermal resistance for convection. And sure enough, the thermal resistance for convection would be 1 over HA, which we derive by using the definition of resistance is delta T over Q. And we know what the Q is in the case of convection because we learned it on week 2 of class. And the resistance of convection per unit area is 1 over H. Now we can calculate walls that have not only multiple layers of solid material, but also that have convection inside and out. And we did the calculation and we learned interesting things. Then we said, aha, how about radiation? And radiation is tricky because radiation is not really proportional to the delta T because it's something to the fourth. However, in many practical cases, we can cut some corners, and as long as we're aware that we're cutting corners, it's okay. And we can use the convection equivalent, the radiation equivalent convection coefficient. And in that case, the resistance of radiation per unit area would be 1 over H of radiation. The physics, completely different. The mathematics are the same, and that's convenient. So now we have defined resistances for conduction through a wall, for convection, and for radiation. And what we saw is that radiation goes in parallel with convection in many cases. For example, if we have a wall and that has some fluid temperature outside and some surrounding temperatures, from the surface of the wall, we have heat that goes out by convection, and simultaneously, it goes out by radiation from the same surface. Because in this case, the heat flow goes simultaneously, is a parallel path. For the case in which the surrounding temperatures and the fluid temperature are the same, which is a fairly good approximation often, then we definitely have a parallel path here. Something I skipped quickly here is we also discussed the week before the break the concept of dominant thermal resistance. That in the case of that is the resistance that gives the most of the value to the final value of the composite resistance. So in the case of series resistances, if one resistance is particularly large, the overall value of the total resistance is dominated by this large resistor, and this resistor will be the dominant resistance. If I have a parallel circuit, for example, the heat losses by convection are much higher than the heat losses by radiation, then is the smallest values of resistance the one that rules. It's the smallest values of resistance because it's the highest amount of heat shortcutting through that path, right? We have to keep this in mind. We discussed all this the week before the break. This is just a refresher, just to get used to some of the words and concepts we had used. I'm going too fast for this to be first time learning. Even the week before the break, we were moving fast already. So in a schematic such as this, we have a wall that has two layers of solid material that has convection inside and outside, and that has radiation inside and outside. A single wall, you can see, can be quite complex. And this is even using the concept of thermal resistance. If we didn't use the concept of thermal resistance, this problem would be incredibly tedious to solve. just by writing a system of equations and solving it. The concept of thermal resistance is very, very, very handy. It's an engineering concept. Physicists just go and do the system of equations. That's why it's engineers, the ones that design cars, planes, and chemical plants. And we talked about, because in contact, we also have that the heat rate, the rate of heat transfer is proportional to the temperature jump between the two surfaces. We can also assign a contact resistance to a thermal resistance to contact. All these things together, now will result in an overall total resistance. So whatever the circuit is, whether it's a circuit for pipes inside a heat exchanger that has fouling inside and outside, or heat losses in a house, or pretty much any other problem that is in steady state, and at this stage we're talking about in 1D, in all these cases, we have that heat is rate of heat transfer is proportional to the temperature difference between the two ends of this equivalent circuit. So this total resistance, we tend to give a name as, by picking a reference area, we have what we call the overall heat transfer coefficient. And here is the definition. So Q is delta T over total resistance, and I can do total resistance as per unit area. And the unit area, I'm going to define it arbitrarily. Typically, if we have a window, we know what it would be. We're going to see today, we can have cylinders that can be small inside and big outside. So we have to pick if it is the inside area or the outside area. We pick whatever we want, but we have to say what it is and stick with it. And that way we can define the overall heat transfer coefficient. This is very important because it's tabulated for construction materials and it's tabulated for heat exchangers. So this is a very general concept that comes from thermal resistance. It's all the resistances together put in one. Where we closed the class on the week before the break was saying, just doing a little bit into the mechanisms of convection. We saw that the equation of convection would give us a thermal resistance of convection of 1 over H. This is thermal resistance per unit area. So this is a mistake, should have a double prime. But we said that in reality, convection is conduction through a boundary layer. We're going to see those concepts in much more detail later in our in the mechanisms of convection unit. But knowing this, knowing that convection is in reality conduction through a boundary layer, that means this 1 over H in reality is an thickness of a boundary layer divided the thermal conductivity of the fluid, air or water. And what we saw is that this boundary layer is fairly thin. And we saw also how for example, in air, if there is no wind, the boundary layer is more or less 3 millimeters thick around our bodies, for example. And in forced convection, if it is windy, the boundary layer becomes a third of the thickness, less than a millimeter, right? We will get much deeper into that, but we can already talk about important aspects of convection from the point of view of the actual mechanisms happening, even before we write any differential equation of any type. And this is as far as we went last week. Oh, in this page, you have the overall heat transfer coefficient for construction materials that I listed it here. You can start designing houses now and calculating the heat losses that you would expect. There is so much power in these equations we're learning in this class. And these are very simple, but so deeply insightful. Good. This was just a warm-up to get into conduction in steady state beyond 1D. I'm looking at the chat, and as I change the notes I'm going to follow, if anybody has a question or a comment, I'll try to respond to it right then.